Yeah, welcome. This is the first technical lecture on the 3D coordinate systems series. Today we will talk about motions and similarities in the plane, because everything in the plane is much more easy than in 3D. First, I want to talk about the notation I use here in this lecture, the objects and their representation. Objects I usually indicate with calligraphic letters, and the representations are usually scalars, vectors, and matrices. So for instance, if you have a point in 2D, then it has either coordinates x, y, or a coordinate vector x. This is boldface in contrast to the non-boldface xy coordinates. Or you have a 3D rotation, r, which is calligraphic, with angles, alpha, beta, gamma, or described by a rotation matrix. Second, I use the notation for the absolute value, the classical bars, for the vector norm, or the length. You see that there's an alternative notation for the vector norm with double bars. That means we use here this with 1. The determinant also with 1 bar, and then the Frobenius norm of a matrix, which is the square root of the sum of the elements of the matrix. And if we talk about stochastical entities, I use the Dutch notation, which underscores the entities. So if you have an uncertain point, it's a calligraphic x with an underline, or if you have a vector which is uncertain, then you underline it. So let's start with the basic 2D transformations. So first we talk about the representation of 2D points. Of course we use Cartesian coordinates, x and y. And you see here the point has the name x, calligraphic, and is represented by this vector or explicitly by x and y. We assume a right-hand system. That means we have a left rotation from x to y. And x and y are these two distances of the points from the two axes. That's very classical, which you know from school. Now, let's start with the translation. We have a translation of this point x to point x prime. That means the coordinates of the new points are different. That means x and x prime are two different positions. And of course, the difference is the translation elements tx and ty. You see, we can symbolically write this as x prime. The new point is the translated old point. The same we have for the rotation. So here we have the point rotating around the origin by the angle gamma. And in order to derive the equations for this, we represent x in polar coordinates. That means we have the distance of the point to the origin, and with cosine and sine alpha. And then the new point, of course, is with a new angle alpha plus gamma. And if we use the trigonometric addition formulas, we get this expression, and then we use r cos alpha here in this expression for x, etc. And we get this expression, and this is obviously linear in x and y. So we can write this in a new form. That means the new coordinates x prime, y prime are a matrix, the rotation matrix, multiplied with our original coordinates x and y. And you see here the rotation matrix has two entries, the same entries on the diagonal, and the same entries but with opposite sign on the off diagonal. So this is, so to say, the basic description of rotation. Again, symbolically, here we have the operator r in calligraphic letters. Now, how do we know what the sign of this off diagonal is? Sometimes you see it here, sometimes you see it here, as in this case. Now let's assume we have a small angle. Then the sign of an angle is close to gamma. That means the rotation matrix is approximately this matrix. So you have a minus gamma here. That means you diminish the x coordinates by a small amount if the point is in the first quadrant. So you see here the point x moves a little bit to the left which is indicated by this minus sign. So this way you can remember whether you have a minus sign here or on the other side. The third transformation is dilation or scaling. So you just multiply the coordinates by some factor, lambda, here. And you can write this also as a matrix vector product in this way. So, of course, we have different cases. So, if lambda is larger than 1, we have a magnification. So we increase the size and keep the origin fixed. If we have a value between 0 and 1, it's a diminution. That means it shrinks to the origin. Of course, if lambda is 0, it shrinks to the origin. If lambda is minus 1, we have a mirroring around the origin. And if it is some other value smaller than 1, it's mirroring and magnification or diminution, depending on whether lambda is less than minus 1 or larger than minus 1. So the problem is now that we have here matrix vector multiplications here, and we have additions here. So this is the reason why we use homogeneous coordinates, and these have also many other advantages. So the first is the problem that, let's assume we have a translation and a rotation. First the translation, then the rotation, or we have it differently. So first translation upwards, rotation around the origin, so we come to this place, or the blue case, first the rotation by 45 degrees and upwards 1 up, we come to a different position. So the blue and the green arrows are at different places. That means we have two different points depending on how we combine the translations and the rotation. So they are not commutative. Question is this example sufficient to say generally this is so? It's likely. The second is, how do we determine the inverse transformation? For translations, of course, we subtract the coordinates, and for rotations, we take the negative angle. But how do we do this in general? This is not easy if we have combined rotations, especially if we have concatenated rotations. The third problem is, what happens if we don't move the point but the coordinates? So here we have a point, x, linked to some object, so to say a small car, let's say, with this point here. And here we have the coordinate system. And if we now move the coordinate system in a positive direction, the coordinates of this point obviously are diminished. So we have a different situation than if we move the point. Question is, how does this situation change the concatenation? We have to discuss this. And finally, we want to join translations and rotations. As I already mentioned, translations are additive, rotations and dilations are multiplicative, and we would like to join them. And that's the reason why we use homogeneous coordinates. So what are homogeneous coordinates? What is their advantage? First, we start with the motivation. So they allow an easy concatenation and inversion. They preserve collinearity of points. So if we have 3 points in a row and we transform them by a transformation matrix, then the 3 points stay collinear. It's easy to join 2 points and 2 lines, which is a topic which we don't discuss here in our lectures. And it's a classical tool of projective geometry. We focus here on angular preserving transformations, that means motions and similarities. We don't talk about perspective mappings, which allows a little bit simplified representation in our case. So, what is a homogeneous element? An algebraic element, a point vector or a matrix, is called homogeneous if for some factor lambda, the algebraic element lambda times this vector or matrix represents the same geometric element. So if the point is not changed or the transformation is not changed, by multiplying the vector or the matrix with this factor, then we talk about E being a homogeneous element. In our context, the elements may be points or transformations, that means vectors or matrices. So let's start with the definition of homogeneous point coordinates. A point x, it's still a point in 2D with non-homogeneous coordinates x, and you see here you have a slanted bold-faced vector, has homogeneous coordinates. Here you have the original coordinates, x, y, the Cartesian coordinates. You add a 1, you get a 3 vector. You multiply the whole thing by some factor w, which should not be 0. And then you get a new vector u v w, and you call this vector x upright. So this is a homogeneous vector because it's an upright bold-faced vector in contrast to this vector, which is slanted. So this contains Cartesian coordinates or non-homogeneous coordinates, and this vector contains homogeneous coordinates. You see the factor w can be chosen arbitrarily, except being 0. But in our context, we can use w equals 1, so we can, in our lecture, can use x, y, 1 as the basic representation of a 2D point. So we still have 2 coordinates for representing a 2D point. Now, of course, we can invert this. Let's assume we have the 3 vector x, the homogeneous vector x given, and w is not 0. Then we easily can derive the non-homogeneous coordinates by just dividing the u and the v element by w. Now, what happens? This is just a remark because we don't use it in the lecture. Let's assume we have a vector uv and the third element is 0. Then of course we can't derive the coordinates x and y. But we can show that this point represents a point at infinity. So if you have a straight line and you move the point along this line at infinity in the direction uv, then this point at infinity is represented by this 3 vector with the third element equals 0. We assume W1, and this assumption is removed in later lectures in photogrammetry or computer vision. Now let's represent our basic transformations using homogeneous coordinates. So let's start with some point u, v, w, and shift it to the other point with coordinates u prime, v prime, and w prime. And then we have a transformation matrix. Now imagine w would be 1. Then of course we just need to add u and tx and v and ty, which gives then the x prime equals to u plus tx, etc. Now this also holds for if you just have general coordinates, that means if w is not 1. But you can also write this equation, of course, compactly as x prime equals some matrix T, which is this 3 by 3 matrix, multiplied with the original matrix, with T consisting of 4 parts. So the left upper part matrix is a unit matrix, the right upper part is a translation vector, the lower left part is a horizontal 0 vector, and the last element is a 1. So it's this matrix. Now the question is, this matrix is written upright. So it's not a slanted T, but it's an upright T. So it's a homogeneous matrix. Why is it homogeneous? So imagine you multiply T with some arbitrary factor lambda, starting from some xy1. Then of course you get this vector u, v, w prime multiplied with lambda. But we know that this is the same for any factor, so we can actually divide by this lambda and actually get the original coordinates x, y from this vector. So the translation is invariant with respect to a multiplication of this multiplication matrix T with some arbitrary factor not equal 0. The same we do with the rotation around the origin. So instead of multiplying with the matrix here having a unit matrix, we include here the original rotation matrix. This is the cosine phi's on the diagonal and the sinus phi's on the off diagonal. And we, of course, get the same result if we have W equals 1 as before. And if we write this in matrix form, the rotated point x prime has coordinates x prime with this homogeneous vector is some matrix 3 by 3 multiplied with the 3 vector homogeneous coordinates of x. And this rotation matrix again has 4 elements. The upper left is the original rotation matrix 2 by 2, and the diagonals are 0 and the last element is 1. Now you see here we really have a rotation matrix, which if you multiply R with its transpose, you get unit matrix. But if you multiply this with an arbitrary factor, you of course get the same rotation, but then of course this upright R multiplied with upright R transpose will not be one unit matrix anymore. So we may have to make a distinction between these upright matrices and these slanted matrices carefully. Again, we look for the dilation and the scaling, and so we just have to scale the first coordinate with lambda and the second coordinate with lambda, and we again can write this in this matrix vector product form. That means all these 3 basic transformations, translation, rotation and dilation, symbolically written in this way for the points x and x prime, and for the operators t, r and d, can be written as a matrix vector product with a 3 by 3 matrix multiplied with a 3 by 1 vector. So we will see that this allows an easy inversion and easy concatenation. So let's look at the inversion. Inverting a homogeneous transformation. So let's assume we have this transformation A given by multiplying the vector x by this matrix A, leading to the new point with coordinates x prime. Then it's inverse. That means we have an inverse transformation, that is A power minus 1, is x equals inverse transformation multiplied with x prime with B equals the inverse matrix of A. So this is very easy. For the individual transformations, we see what happens. The inverse translation, of course, is just here minus t. Here for the rotation, we have here the rotation matrix inverted, which is identical to the transpose of the rotation. And here the dilation, it just takes the inverse of the factor lambda, which we could also write in this form, putting the lambda here, but we will not use this property. Now let's have a look at concatenations. They take us into some problems which we will see immediately. But let's start. So let's assume we have 2 transformations. I call them M1 and M2, and they are represented by some matrices, 3 by 3, M1 and M2. You could imagine these are motions, but they may also contain a scale. So if we first apply M1 to our point and then M2 to the transformed point, this is so to say the concatenation of M1 and M2 from the left, then we just have x from the left multiplied with M1 and then the product multiplied with M2. So we have the combined transformation matrix being M2 multiplied with M1. So let's look at what happens if we have a similarity for this concatenation. The reason is why I write this down is to see the difference between the classical coordinates and if you explicitly work out the algebra. So let's assume we have a similarity transformation. So we first dilate, for instance, scale with some factor lambda, then we rotate around the origin with some angle phi, and then we translate the enlarged and rotated object by some translation. Then we can easily see that this matrix does this what we want. So we have here the translation vector, we have here the scaling and all coordinates, and we have here the elements of the rotation matrix. Sometimes it's useful to see that this matrix has a special structure, namely that lambda cosine phi appears here twice, and lambda sine phi appears here twice with different sign. So if we replace these two elements by A and B and take the translation vector as CD, we can write this similarity transformation without any trigonometric expressions, which sometimes is very useful. So what is this all useful? We want to use these transformations for describing poses. We have here an object, let's say a car with the coordinate system here, and we want to know where is this car in this coordinate system. And we always assume that a point, sometimes you don't need it, but here it's very useful, that each point has a coordinate attached to it. So we have this point with the origin of this coordinate system in this car, let's say the car coordinate system, and the x1 and the x2 axis here. And we want to describe the transformation from the coordinate origin E0 to x0. And of course, we also want to know how the rotation or possibly scaling looks like. So this is actually what we described just now. So we can use the frames as coordinates, as describing coordinate systems, like here, x and y, or as coordinates attached to some object which is moving, depending on the application. So let's assume we have a frame. We describe it by some rotation and some translation. We could also include a scale, which I don't do at the moment. Or we could say the frame consists of 3 points, as we saw this here. So we have the origin and the 2 unit vectors in x and y direction. So in general, we have some rotation matrix and translation vector, but here we would have no rotation and no translation. So if you write it out, you see here in homogeneous coordinates, this is here up the upper matrix, this is rotation, which is a unit matrix. We have no translation and 3 ones in the lower row, because these 3 vectors are homogeneous vectors. So the column vectors of this matrix actually represent the 3 points of our coordinate system. So a similarity transformation of a frame, of course, could contain a scaling, a rotation and translation, as we saw, and we always interpret it as a motion of this coordinate frame into a new coordinate frame. So these 2 frames are different, so to say, as part of a moving object, as if our object would be first here and then moved to here. So let's look at a frame which is moving twice. So we start with the first similarity, which depends on lambda, the scale, the angle phi, and the translation tx, ty. So this is this matrix, which represents this similarity. After the first similarity, we get the new frame f prime with 3 new vectors, E1, E2 and E0 prime, which is nothing else than the multiplication of S1 with F. That means S1 is multiplied with E1, S1 is multiplied with E2, and S1 is multiplied with E0. And if you multiply this out, because we have a special matrix, we arrive at this matrix. You see here the new points all have a 1 at the third value, and we see here the translation of the origin to the new point, and here we see that the point is scaled and rotated and translated. That means the axis, the unit vectors of the basic frame are transformed in this way. So this is easy. Now let's assume we have a second similarity with some factor mu, with some rotation psi and some translation vector ux, uy. So this is this matrix. So we have here mu cosine psi and ux, uy, etc. And now we have to multiply the already transformed frame, the new frame f prime, with this matrix. Now let's do this. Aha, this is this matrix. This looks a little bit awkward. So because we have already complicated expressions here, we possibly don't want to have the plus here, and that means the origin is multiplied with mu, and here we have the translation vector transformed with some angles and sine and cosines and the translation. So these equations become easily horrible. That means we would not like to do this in the following. That's the reason why in the following we will not write out the content of all these matrices, but only work with the matrices. And if you do some programming, you of course use the programming language and its tools to handle matrices, like in MATLAB, in order to do the transformations using these types of multiplications. And then afterwards you read out the numbers which are achieved by this. So, what have we arrived? We have seen that if we use homogeneous coordinates, they are interpretable. The scales multiply, the rotations add, the first translation vector is transformed. That means we get a translation vector which is also transformed by the second translation and rotation. And this is not very transparent in general. What happens if we have 3 or more transformations? What happens if you want to have the inverse of this transformation? This is really awkward. That's the reason why we should not go into the details of the algebra within these matrices. In the next lecture, we will look at 2 different topics. First, we assume that not the object is moving, but it is passive and the coordinate system is moving. And we look into transformations which don't refer to the origin of the coordinate system, but to some local coordinate system which we have reached in the meantime. So this will be the topic of the next lecture. Thanks.